So anyway, that's just kind of my philosophy. All right, now, last time we were doing two-dimensional, I don't really want to review too much. We did two-dimensional, a particle is trapped in a ring. Can't go up or down, whatever. I mean, these are all kind of BS type, model systems to get you better at this, right? Get your math under your belt. And I mentioned how, as usual, some 17th century mathematician solved the damn thing. Okay, then we went to 3D, and as usual, the kinetic energy operator is the problem. And be careful, remember we have two M's now. We have an M sub L, which is the azimuthal, and I don't know if I'm pronouncing that correctly, quantum number. It's the phi quantum number. Now, through a process that you have already gotten a taste of, in terms of converting dx, dy, dz, all of that squared, you then have to convert that to r theta phi. You basically did that for cylindrical coordinates. And of course, if you did this for fully spherical, I think you could do it. It just would take you an extraordinarily long period of time. That's a phi squared. And this is what you get. Notice I never write these three things in the same order, so that doesn't mean anything. I'm just not being careful. Okay, so again, kinetic energy operator in 3D. Bismarcker to solve, but it's all just a bunch of algebra, but I mean like a really large amount of algebra. Then we whittled this down a bit, so I'm just doing a little review. And by whittle it down, we used a separated trial solution, but we did something a little funkified, where I said that I'm going to use a function of r over r. Notice that the function of r could contain r, so as I'm always emphasizing, I'm not deciding ahead of time what the result is, because r of r could be r, right? So it wipes that out. And of course, the reason we do this is because it's going to simplify things, simplify them such that we can look in a 17th century math textbook and find that, in fact, someone answered it in 1600s or whenever. Okay, so, and note that, of course, the spherical harmonic is itself a theta function and a phi function separated. There's nothing like sine of theta plus phi. That is not separated, and that's not an answer. Okay, so when we do that, what we got was, a bunch of algebra. I wrote it all down last time. I'm not gonna write it all out again, all the steps. Well, there's only like two. The main thing was that there was some simplification, some multiplication of h bar squared over 2m, some rearrangement. What's important about this is that what we've got ourselves is a separated solution. I'm assuming a radial potential, because potentials that aren't functions of x, y, z are rare. And potentials that are function of angles, I don't know. I don't think I've ever seen one. And so we're just going to assume it's a function of the radius. Of course, if this was a hydrogen atom, it's 1 over r. Minus 1 over r. Actually, minus 1 over 4 pi e naught, the whole Coulomb's law deal, the constants for Coulomb's law. One thing, I don't know if I've mentioned this before, but one neat thing you can do is if you work with a system of units where a nanometer is, instead of a meter, right? So if you see a meter, you can just write down the number 1. If you have an equation that says plug in the number of meters here, and you're dealing with 1 meter, you just type in 1. Well, you can have a system of units where that's true for a nanometer. If it says plug in distance here, it says psi. If it says plug in distance and you're dealing with 1 nanometer, you can plug in 1. So that's what I mean when I say the units of length are nanometers. Okay, so you plug in nanometers. Nanometers are your unit of length. And let's see, the mass of an electron is 1. All right, so instead, if you see an equation that says plug in mass, and you have a mass of 1 kilogram, you plug in 1. All right, but in a different system of units, a mass of one electron, whatever an electron is, 9.1 times 10 to the minus something something, 10 to the minus 31 kilograms, that's the number one. Okay, so an electron's mass is one, a meter is one, 1 over 4 pi E naught, that whole Coulomb's deal, that's one. H bar is one, the number one. Now, that's a lot of, you can imagine like, well, hold on, what if you created a circle that doesn't bite its tail? In other words, how can I have mass of an electron 1? How can I have length of 1 nanometer and H bar still be 1? How can I do that? That works, but here's where you take a hit. Time is in 10 to the minus 17 seconds, and energy is in a unit called a Hartree rate. Now, the point of that is that, imagine I'm doing quantum mechanics on an electron. There's no constant here. And you can imagine there's equations. Coulomb's law, 1 over 4 pi E naught. That sucks to keep track of that. Well, it's not there. Those are called natural units. All the units go away. All you got to remember is that energy is in Hartrees. So anyway, you should know that. Okay, so now what? All right, now we've separated everything, and it turns out that we did go to our math friend. Yeah, remember that these have to be constants. Each one is equal to a constant because I've got a bunch of r's, a bunch of thetas and phis. It's a differential equation, and remember the idea here is that a change in r can't be matched by a change in theta or phi. They don't talk to each other, and that would be required when I'm talking about how things change. If instead all of this is equal to a constant, then this is equal to a constant, and then you don't have to run into that weird idea of something expanding and then rotating differently, right? Which just doesn't make sense. Okay, so the mathematicians have some idea how to solve this back in 1700. You can show that this thing is equal to a constant. You can show that the phi guy is separable, and then you assume that the wave function is what we saw before, e to the im phi. And then you mathematicians figure out to set the constant equal to L times L plus 1, where L is a new quantum number. And then they can figure out the wave functions, which are a function of L and m sub L. And I think we talked a little bit about this last time, right? Spherical harmonics. It always gets this symbol. You'll always see this symbol. And you're going to get e to the I m sub L phi times some kind of function of theta. And did I write down the giant equations for the spherical harmonics? I think I did. Square root of 2L plus 1. Did I? Yeah. Anyway, so that was hideous. And I don't want to really say anything too more about that. You just look them up. Whenever I need a spherical harmonic, I just Google it. It's not hard to find. Okay, so now let me just wipe this out. And I try not to do this too often, but it's too tempting. So knowing that this thing's a constant, like I say, I wouldn't be surprised if they work backward. I find it funky to set it equal to a constant. I find that a very strange thing. A constant of the nature of L times L plus 1, but I think they knew ahead of time that there would be quantum numbers are really like bookkeeping tools. You have, they find the solution if L is 0, they find the solution if L is 1, if L is 2, anyway, and then you have m sub L 0, and then you've got minus 1, 0, plus 1. Right, these are the solutions that they find, for each. Anyway, so, and hopefully you saw that as a grad. I'm kind of being a little too dismissive of it. Okay, so now let's manipulate this thing, and what you get is, so I'm unpacking the previously separated wave function. I've got a k. A k is going to be square root of 2me over h bar squared. And I'll write that down for your notes. And then we've got minus L times L plus 1 over r squared. So I've divided by r squared. I've done some algebra, but it's very trivial. Okay, so again, I've multiplied by r, the function I'm looking for, and I divided by r squared. And this is what you get. And then, of course, k is square root of 2me. Damn thing always shows up. Always shows up. Never get rid of that thing. But it's kind of nice because I'm comfortable with it. Whenever I see a k, even at talks, when I see a k, I'm very comfortable with it. Okay, and it doesn't look hideous. It's less scary. And all you have to do is plug in your potential. And if you plug in 1 over r and you use natural units, you're going to solve the hydrogen atom. If you plug in, which what we're going to do, if you plug in, then you're doing particle in a sphere. Particle in a sphere. So I should put some qualifiers on here. And as usual, I know I was a little inconsistent with whether my trap was A or L. L is kind of more natural to, I guess, our English speakers, but it's also more traditional to see in quantum literature to call A the size of whatever trap we're talking about, which of course is always a source of boundary conditions. Now I'm also going to, so I'm doing this, I'm also going to say L equals 0, so I'm solving in an S state, which is obviously going to be a ground state, and ground states are always the most important. And so the reason I want to bring that up is, look up there, watch this. You're hopefully would kind of laugh at this point when you see what's about to happen. Plus k squared r sub r. Okay, well, v of r is 0, L is 0. There you go. Have you seen that before? Double derivative is equal to minus the k squared times the function, right? The solution is a e to the, you guys do recall this, right? You have seen this equation a zillion times, just not with r in it. You've seen it with x, right? But what does it matter? Those are just letters. The solution is automatically a e to the I k, not x. I did an x. I didn't need to. There's no x. Plus b e to the minus I k r. Right? Double derivative. The function survives it. You just end up with a minus I squared k squared. Plus k squared is equal to 0. Right? So there you go. Okay, now we took our three-dimensional kinetic energy operator, we whittled it down, and then now we put in some specifics to our problem, and then we make it again something that you probably had learned in Calc 2, how to deal with this. And we dealt with exactly this. We just had an x instead of an r, but that utterly doesn't matter. Okay, so now we have the wave function. So now we want to get the energies. Well, we want to get A and B. Need to get A and B, and then we can get the energies, right? So as usual, we have to set up the problem. We solve it. We're not quite done solving it yet. And once we do solve, we have to get our A and B. Once we do that, then we'll get our energies. And at that point, there's really nothing else you can do. Now, to solve this thing, as usual, you need boundary conditions. Because that's always the source of quantum. The quantum and quantum mechanics comes from boundary conditions. And we have two. A is R of R is at at r equals 0 is 0. And then, of course, the one, just like particle in the box, r of r at r equals a is 0. I mean, look at it, it's identical to a particle in the box. Not the centered blocks. I did the centered block problem where the left-hand side was minus a and the right-hand side was plus a. This is more like the sine function where I had the left side at 0 and the right side at L, or in this case A. Okay, right, so because at r equals a, the wave function has to hit 0 because it can't continue further because it has infinite potential. What about that? Where's that from? What do you think? The set of particle in the box had to be 0 at the origin because to the left of it is infinity, infinite potential. Is that true of a sphere? Is that true of the center of a sphere? Remember, I'm talking about the dead center of a sphere. Why can't the particle be in there? You're not going to guess this. Wait, anyone want to try? Yeah? Want to try?
For an atom or just for like?
Well, no, I mean, it's a part, so I can't say it's an atom because I don't have a Coulomb potential. I have no potential. It's a particle in a sphere. It's an electron inside of a container that it cannot escape, but inside is free to bounce around like an idiot.
Is it because it has to be symmetrical, so the center has to be a node?
No, it has to do with the fact that R is not the answer. Now, sometimes when I have tests in my undergrads, and like, what's the answer? And they're like, Jesus. And I have to give half credit. So
No, you don't.
I wonder at Liberty University what they have to do there. But anyway, this is so. I just wanted I want to keep you on your toes. This is the real answer. That's the real answer. And remember, I said this. Remember, we did this because the mathematicians who figured this out knew that you got to a way easier equation this way, which is an easy solution to this equation, but this actually isn't the real deal. You have to remember that it's been simplified. It's not correct. This is not the real Schrodinger equation. It's been simplified. The hint you take is that you've got to remember to do this at the end. I've changed the problem, and so therefore I did not get the solution. But to get to the actual solution, it's not hard. I just divide by r. Okay, now at r of 0, you see what I got? I got a singularity. Right, I got 1 over 0, and that's not allowed. The only solution is for r at r of 0 to also be 0. So that's where that comes from. Anyway, I just wanted to point that out. That really slays people that happens. Okay. So therefore, a plus b equals 0. Therefore, a is equal to minus b. Therefore, the ground state, L equals 0, is, it's not normalized, but whatever, sine of kr. Over r. Don't forget the over r. R of r is sine, but the wave function is that result, which is sine over r. So that's the result. Okay, now as usual, the argument cannot have units. Anyway, so you can figure that out from here. And let's see, I think that's about it. Okay. Oh, this one. Okay. Right, we're supposed to get to the energy. Okay, so let's see. Sine of Ka equals 0. Right. So that's like the real. This is kind of a slick willy boundary condition. It is necessary. I mean, it's important. It's essential. But this is like what we think is the real boundary condition, because that's where the potential goes to infinity. So the wave function better be 0. And so therefore this has got to be equal to n pi. Therefore, k is equal to n pi over a, and k being the square root of 2me over h bar. Therefore, E is h bar squared. Energy is actually h bar squared k squared over 2m. So h bar squared n squared pi squared over 2m a squared. There we go. Where n is a radial quantum number. And let's see here. What do I want to say about this? And well, you can normalize the thing. Yeah, let me point out. So I should kind of be saying that this is an approximate solution. I want to just remind you one last thing about 3D. Then we're gonna kind of quickly go on. So we're done with all, everything I've been doing at the beginning of this class has kind of been a review plus, right? So we're finally going to get into real quantum today, graduate level quantum, physics type quantum with Dirac notation. So I'm just trying to, get you thinking about waves and whatnot, and make sure your math is, again, we value that. But I do want to point out that this one's kind of important because a lot of people forget this. To normalize this problem, I forget this a lot. Like the first time when I got to teaching quantum for the first time as a faculty member, I actually messed this up really bad. I'll show you what I did here in a second. So be careful of this. This will get you. Why don't I just, I don't even know why I'm doing this. Everything is, there we go. That works. Okay. So I want to normalize it. So we need to integrate this SOB, and we'd like it to spit out 1, but it won't. It'll spit out like a squared, so then you got to divide by the square root of whatever that is in the actual wave function. Here's the thing I want you to remember. R squared sine theta Jacobian d theta d phi dr, or whatever, dr d theta d phi. Oh, wait a minute. No, the order matters. Order matters, right? Because they actually line up. They line up with the limits. So you actually have to get that right. And so, again, what you do is you figure out what constant squared makes, what constant squared makes that true. So there's not much to say about that. Again, though, I did want you to remember that when you're integrating 3 dimensions, never forget your r squared theta. Because remember the point here is that dx, dy, dz, we're doing a triple integral, and integrals have dimension. And so if I have dimension times dimension times dimension in 3 different dimensions, I'm describing a cube, right? The cubes have volume. A change in R, a change in theta, and a change of phi doesn't actually describe volume. It's close, but it's skewed. For it to turn a change in R and theta and a phi, to turn that into a perfect cube, you need to multiply it by R squared times sine theta. And then you're getting a proper volume type of integration. Let's see, last bit. So if you look at the other solutions to particle in the sphere, let's look at, so you run into, I won't say too much about this because you run into the exact same thing that you ran into with the particle in a ring, the 2D problem. So I'm going to look at the L equals 0 solution, and what you find is, now remember I got to make this stop at A. What happens is, So remember that what I've done here is for L equals 0. But notice that I've got a radial quantum number. So obviously this is an N is not allowed to be 0. It's got to be 1, 2, 3. And I know that because of the way that it's solved. But number 2, I know that you can't have zero energy. It's not allowed. It's actually an uncertainty principle, which we're going to be discussing later. But you cannot have zero energy. Because then I would know how fast, I know where it is and how fast it's going at the same time, and I'm not allowed to do that. Okay, now we can have I've just drawn a 1s state, but you can have a 2s state and a 3s state, and the way those would look, I actually bothered to plot them on my computer so that I wouldn't vomit this out. Does this, okay. Okay, so, an obvious start. 1s, 2s. Notice that it's got a node, so sure it's got a node, and therefore it has higher kinetic energy. But what I want to point out is that, okay, if energy is higher, K is higher, I believe it. Anyway, K is higher, and so as the wave travels from 0 to A, it has a shorter wavelength because K is bigger. Remember that the sine function, the innards, K is 1 over wavelength. So if K is bigger, the wavelength is smaller. And this 2s wavelength is shorter than the 1s. Remember that a shorter wavelength is a higher frequency, and a higher frequency is a higher energy. Now you follow along all that? Stream of consciousness, I know, but okay. And then a n equals 3 state is real kind of hideous, does like that. Okay, that's a 3s. So anyway. Yep, okay, and then, so you know how to get those guys. When it comes to, here real quick, and we're going to get to the Dirac notation. When it comes to the P states and the D states, and no one really ever worries beyond P and D states. Not that these are atoms, right? This is not an atom because you can have a 1P state, you can have a 1D state. So I'm just going to draw some L equals 2, 3 wave functions. The way these things look is, again, they do like this. And so, so what you're looking for is where are the nodes? And so, if this is a P state, you have to make this point, which is like 3.14 or something like that. You have to force it to actually equal A, like we talked about last time. You do that by manipulating the definition of K, which is the same thing as manipulating the definition of energy. And then you'd have a 2P state. So remember, it's unusual because you can have a 1P state. 2P state, you do that by adjusting K such that this second crossing is at A. The other states, the D state is actually kind of the same. It's just longer wavelength. So this is like a P state, this is like a D state. They actually don't really look any different, so it can kind of get a little confusing. Now, when you're looking for those zeros, like where are these crossings, if you Google it, because of, you can imagine how important this is. These are solutions to a bunch of problems. What you find is tables that look like this. Right, you've got your SPD states, and then you've got your radial quantum number, and then you find where the zeros are, and then again, like I discussed last time, you just make sure that your K is defined such that K times A is will be equal to 0. The function will be equal to 0. So anyway, I discussed that last time. Now, one reason I also wanted to spend some time on this, not too much, as much time as I did, was because particle in a sphere calculations are universally used to describe nanomaterials. So we think of nanomaterials as often being quantum dots, as being round, and then we think of the electrons inside of them as being like just free, so that they travel with no potential until they get to the edge of the nanomaterial. It actually does describe a lot of spectroscopy. The person who thought of that was Lou Bruce, my advisor's advisor, should win a Nobel Prize this year, is scheduled to give a talk, although I know this whole Zoom thing is weird, and I'm guessing that's either the talk's not going to happen. We have a talk next Thursday. So we're getting back to regular seminars. It's weird. I mean, this is so weird. But I mean, I don't know what else to do. No one's invited me anywhere. But, so Lou Bruce is supposed to speak, and again, when it came to, he was looking at semiconductors, he realized that there was this structure, let me do this in wavelength. Remember, wavelength is 1 over energy, it's a real pain. So when you look at certain types of semiconductor nanomaterials, he saw this progression, he saw these distinct peaks, whereas the bulk is like this. So this is bulk, and this is a QD. Okay. Now, and he discovered it, some guys in Russia discovered it at the same time. There's an increase in energy between the bulk and the quantum dot's first absorption. And so what he figured out was that when you excite it, and then the electron goes into the excited state's higher energy. So it takes shorter wavelength to reach that. How much? Well, particle in a sphere. Particle in a sphere says if the sphere is smaller, the energy gets higher. So he had made a size series of these things, and he found that big ones had absorption onsets close to the bulk, and small ones were further away. And he said, well, the material is smaller, the electron has a higher energy because it's like a particle in a sphere. Also, S, P, D, on and on and on. And then there's actually some like little sub-wiggles where you have to do some like real clever spectroscopy to see some of these other little features, and so that's like a 2S state and whatnot. So anyway, he was able to map particle in the sphere states almost perfectly to the absorption spectrum of these they were actually semiconductors. He was able to match them almost perfectly. And that was kind of, I mean, it's actually amazing that it works that well, because it really shouldn't, but it does. And he derived, therefore, an explanation about how all of these things work. That's why I was telling you earlier, even in my professional profession, I actually use particle in the sphere calculations all the time to describe the features I see in my materials, which are, of course, a little bit more advanced than just a single, like core shell materials, and so I have to do these calculations. They're a little bit harder. Actually, I was going to put that on your first exam. But anyway, so again, I wanted you to see this because of all of you who are working in material science, you may very well end up doing these calculations. So any questions? Y'all kind of look half asleep. No coffee. All right, well, let's just take a radical departure. And now we're definitely in grad school. And I remember I said to you last time, you need to be reading your first chapter. The first chapter, you don't need to read the whole thing. The first chapter is like 60 pages. That book is only 5 chapters long, something like that. And the first 2 chapters are like 100 pages. It is, I know, extraordinarily difficult to read, but I think you need to read the first 10 pages relatively soon. I'll look at the book and I'll put something up on the website. I don't have it mapped in my mind like page to page. But what you do is you learn the basics of Dirac notation in chapter 1. All right, so Dirac notation, derived by Dirac, when Schrodinger, Heisenberg, some of these folks, when they first published on the concept of this stuff, fine, Dirac is the guy who made it work. A lot of the, so there's a little thing, let me point this out to you, right? So let's take the x operator, which is just x times the sine, like kx. Like, remember that eigenvalue equations, this needs to yield a number, like, I don't know, like 5 or something, sine kx? Well, it doesn't, right? X is just x. What the hell? right? And so even for an operator like where are you, quantum mechanics, eigenvalue expressions, they seem to fail. Dirac is the guy who figured out how to make this work, and I will show you that. By the way, it's a directive. You're using the wrong wave functions. That was his solution. Dirac delta functions are actually the position wave functions. He made all the little Bisnocker stuff that didn't make sense, he made it all work. So that's why Dirac's important. Okay, now we're going to have to get used to certain symbols. Okay, let's talk about, let's do our A e to the I kx. I'm not going to say too much today because I'm kind of running out of time. And I mentioned this to you before, but here's how the symbology works. Wave functions that you've seen in undergrad, and we've had plenty of, it's always e to the I kx. It is now this symbol. This symbol is now a wave function. All right, so you got to get used to it. Okay, now let's take another Bisnocker thing. Oh, I just did it, right? Psi star psi, wave function squared. This is this in Dirac notation. What's cool about that is when you see this as we do derivations, you can automatically put 1. You don't have to, e to the minus r over a naught sine theta, the square root of 1 over 4 pi, which, by the way, I think I actually got that right. That's actually the one that's way. Anyway, you don't have to actually do anything. When you see this, you just write 1. It's like a billion times easier. Okay, now take expectation values. Let's do expectation value of energy with the Hamiltonian operator. And let's just say that's a single dimensional. That looks like this. So I hope you're, we're going to be going over this. I'm just giving you an idea for what it looks like. That is this. Okay. And now, unfortunately, so sometimes we run into shortcuts, and they're awesome. They are unbelievably awesome. Quantum, half the freaking time, this is what you run into. And when you do it with Dirac notation, half your integrals disappear because these are half the answers, and you don't have to do them. But sometimes you do. When you run into this guy, you have to actually, what I have to show you is how to convert it back to this notation. And then, unfortunately, then you got to pull out your Mathematica and work with the wave function. So you're not totally free. But I swear to God, this right here, this makes it worth it. That alone makes this worth it. Half of the stuff you got to learn is gone. Okay, now, this is a state. A state of matter. It has to be matter, not a state of thought. It's not herd mentality. And you get that, right? So Trump said that we're all going to be free of COVID because of herd mentality. He literally said that. Anyway, okay. I'm not supposed to talk about that stuff, but anyway. Okay. So this is a state of matter. It's also called a state vector in Hilbert space. Where Hilbert was a mathematician. Okay. In Hilbert space. Okay, Hilbert space is a fancy way of saying something really simple. All right, so if we're talking about like real space, like this, Hilbert space is X, Y, and Z. Right, where is my cat? Well, she is 5 meters this way, 10 meters to the left, and 100 meters up because I live in a high rise. That's where the cat is. And I know where the cat is because I have 3 vectors in Hilbert space that define perfectly. So you may be thinking like, well, okay, so Hilbert space is just Cartesian space. It's just X, Y, and Z. Not necessarily. What about electrons that are spin up or spin down? Alpha, beta, up, down, whatever. Hilbert space is up and down. So there you go. So it can be different things. The main thing is just that it describes everything that you could run into. Now let me give you a good example of when you'll hear this term, span the space of Hilbert space. You're going to hear that a ton. In talks, in the book, you hear it all the time. Here's what it means. Take particle in a box, and let me draw some wave functions. Now, unfortunately, it would take me literally forever to draw all the wave functions. It would literally take me forever to write all the wave functions because there's an infinite number. But here's the thing. I can sum those states times some coefficient, okay, equal anything. And I mentioned this before. So I get Kitty to draw a wave function, and God knows what she'll do. She'll draw, well, I guess I technically have to have it go to 0. Yeah, I can't, there's some things I can't violate because it's unphysical. Okay, so I still have to follow some basic rules. But here's what it means to say that these span Hilbert space. There's nothing I could draw, given some minor limitations, that I cannot recreate by simply summing enough of these states. Hence, the states span, that means recreate whatever, the Hilbert space, and that's just, in this case, the x dimension. So there's nothing I can draw in the x dimension, that's Hilbert space, that is not spanned, that means can sum to equal, yeah. So anyway, that's what spanning in Hilbert space means. Okay, now, we're going to start with quantum mechanics, talking about spin up and spin down. Because you're going to get a lot of the rules of statistics. So remember, quantum is really it's really statistical mathematics, but on things that are real. Like statistics, which are, I don't know what about. So, and I know I said this at the very beginning, I was talking about diffraction of matter, and I mentioned silver atoms, and people have actually diffracted all kinds of things, particularly C60 at MIT, which was a big deal. But what the Stern-Gerlach experiment, 1922, so Stern, and again, you hear, at talks, I hear this all the time, Stern-Gerlach. People say, I took a Stern-Gerlach approach, or these are Stern-Gerlach effect. This is a Stern-Gerlach wave function. This is what they're talking about. All right, I'll work backward. Okay. Hot silver atoms. Barrier. Very narrow barrier. Probably gets created with a lot of silver. And of course, these things are hot, so they're moving around. They're in a vacuum. And sometimes one of them will just go right on through if it's lucky. What it runs into is a magnet. Okay, so there'll be a north magnet, and then you do something kind of creative here. I have to test my ability to draw now. You create a magnet that kind of looks like this. It's like got a little taper. Well, that north is looking awful. What's wrong with that down there? I have to make it imperfect or the word will blow up. Okay, so you create a little magnet with a taper. It just makes it work better. And then you've got yourself a detector. And you should be used to seeing a detector drawn as an eye. Not like a broken eye, but there we go. Okay, then you've got yourself a detector. Now the thing is that silver atoms, so we're going to assume they're neutral, have a krypton core, state, 4d10, so no free d electrons, 5s1. So it has a single unpaired electron that has a spin of, so a spin of 1 h bar. 1/2, what the hell? Yeah, spin up, spin down, plus half minus half. So that means that it could either be spin up or spin down. And what that means is that when it goes through this magnet, instead of just shooting on through, which doesn't happen, it'll either go one way or the other way, depending whether it's spin up or spin down. So they're little magnets. Now again, ballistically, you'd think it would just go on through, and if you were next to say no, instead they go up or down. So they're little magnets. If you literally could make little magnets, they would do exactly the same things, and they knew that atoms were magnets. Okay, anyway, so that, I know you gotta go. So what we're gonna do is start describing these with kets. This is called a ket, by the way. And we're gonna learn how to analyze the kets for whether they go up or down through the magnet. And then what we're gonna do is take the magnet, which is up and down, and we're gonna turn it 90 degrees and see what happens there. And then you're gonna learn all this.